All right, so all bond lengths are equal, right? And you can see it again with that system.
Dr. Russell, you said you put it in the chat.
Yes.
I don't see anything.
Are you on a device or are you on a laptop?
I'm on my iPad, but I thought you did this last time when I saw it. I thought, but I can get on my
Yeah. It's
I'm
on
just fine.
it's in Blackboard in the assignments folder. If you click the aromatics folder that's in that folder, it's right there.
Okay. All right.
Yeah. All right. So all of the bond lengths are equal. And then there's also, if you think about it in terms of molecular orbitals, you have 6p orbitals here, right? One on each carbon. And if that's the case, if you have 6p orbitals, how many molecular orbitals would you expect to exist for a benzene? If you have 6 atomic orbitals, how many molecular orbitals would you expect for benzene? And how do we determine the number of molecular orbitals that are possible for a given pi system?
Is it 6 orbitals?
Yes. So there are 6 molecular orbitals for benzene. So benzene is considered it is a 6 pi system. Right, it's a 6 pi system. Right. So when we think about molecular orbitals, benzene does not follow the conventional MO diagram construction either. It's a totally different type of molecular orbital diagram, which we're not going to get into here. That's probably for a more advanced study, but it is a 6 pi system. All right, so when we think about aromatics, this is the perfect aromatic. All right, and then we look here. There's some criteria that you have to meet in order to be considered an aromatic. Right, first thing is that the molecule needs to be planar. Right, what that means is that it's flat. That's on purpose, because if it's planar, right, it doesn't have any flakes in it. Right, and that matters, because if it's not planar, then one of these rules is not going to be met, which is the rule of it also being fully conjugated. We talked about this before, and I'll talk about why that matters in a second. Right, but if it's planar, that means that all your orbitals can properly overlap. Right, an example is here. Right, that's this system down here, this 10 carbon system here. Right, if you look at the p orbitals in this system, these all overlap with no problem. Right, but these down here, the orbitals in this part are perpendicular to that system, so they do not overlap properly. So that's going to destroy the conjugation. Well, full conjugation. Right, it's going to destroy conjugation. So being planar matters because the other criteria of being fully conjugated, if it's not fully conjugated, then it is not, it can't be an aromatic. Like, so for this system right here, it might be conjugated, but it's not fully conjugated, right? Because the other orbitals in that bent part don't overlap. So you'll have a part of it that's conjugated, then you have another section that's conjugated, but the whole thing itself is not fully conjugated. All right. The other part of this is, and these are, and let me say this too, these are classical rules for aromaticity. The other part is that it needs to be monocyclic. What that means is one ring. Obviously, we have several exceptions. One right here, right? This is naphthalene. Right. And naphthalene is, you probably have, if you have grandparents that are older than 70, maybe, you may have smelled this, or if you had great grandparents that you knew that were alive when you were young, you probably smelled this in the house, right? This used to be the principal component in mothballs, which older generation swore by. Now it's different. It's a different compound, but it's still an aromatic. But naphthalene itself is considered aromatic, even though it is not monocyclic. Right. The other part of this is the 4n+2 rule. Right. So these four things together kind of help us to identify what's aromatic and what's not. So the other part of this is the 4n+2 rule. So this is a little bit tricky. So we're going to actually go through these and look at what this means, right? So let's start with benzene. How many pi electrons are in benzene? So every pi bond has 2 pi electrons. So this is every pi bond is composed of 2 pi electrons. Right. So how many total do we have here? This is 2 electrons here, 2 here, and 2 here. How many is that total? So benzene has a total of 6 pi electrons. So when you're applying the 4n+2 rule, you take that 4n+2 and set it equal to the number of pi electrons. That's for any system that you're trying to determine if whether or not it's trying to determine its aromaticity. So this is going to be for benzene, 4n+2 is 6. Now you just solve for n. If n is a whole number, then whatever that molecule is, it meets this criteria for aromaticity. All right, so 4n equals 4, n is 1. So this n has to be a whole number. right? And has to be a whole number in order to meet the 4n+2 rule.
I have a question.
Go ahead.
So in what case would n not be a whole number?
Let's say if you had, let me see, if you had 12 pi electrons, right? So if we say, and that's a great question. And let me say this. So this would be let's say 4n+2 was 12, right? N in this case is going to be what is it, 2.5? Is that right?
I'm gonna take your word for it.
If 4n equals 10 and 10 divided by 4 would be 2.5, right? So that's a fraction, right? 2.5 is the same as 5/2. So again, it won't be a whole number. It has to be a whole number integer in order to match or meet the 4n+2 rule. Let me put that in here. That's a good question, right? So if it's not a whole number, then it doesn't satisfy that requirement. But for benzene, it does, right? This is 6 pi electrons. And so we can say that if n is 1, it's a whole number, it satisfies the 4n+2 rule, and benzene is aromatic, right? Let's look at naphthalene. How many pi electrons are there? We're all of the understanding that even though naphthalene is bicyclic and is not monocyclic, it still falls into the category of being considered aromatic. So what about naphthalene? Does it meet is it fully conjugated? Let's answer that question. We know it's flat because those two rings fuse together, right? These two carbons right here are both sp2. And so they're going to keep that ring rigid. There's no flex in that ring because of that bond angle of 120 degrees. That system is completely flat, completely planar. So bypassing the monocyclic rule, because this is obviously an exception, is it planar and is it fully conjugated? We can test for the 4n+2 rule in a second, but is it fully conjugated based on our definition? And this is not the first time we've encountered this definition about full conjugation. What that literally means is that there's a p orbital on every carbon.
Yes.
Okay, it is, right? And we can write them in, we can put in, if we find each pi bond and just put a p orbital on each carbon in each pi bond, you can see that it's fully conjugated, right? No problem. Now the question is, does it meet the 4n+2 rule? You got 5 pi bonds. How many pi electrons do you have? It's always going to be the number of pi bonds times 2. So you got 10 pi electrons. So 4n+2 is going to be set equal to 10, and n will be what? If we solve for n.
2.
Say again.
N will be 2.
2. Good. Right? So n is a whole number. That means it meets the 4n+2 rule. So naphthalene is indeed an aromatic, right? It meets all the criteria and it's an exception to one of them, but it's still considered an aromatic. All right, if we look at the next molecule, which is we've seen this before. I think I showed you this when we first started talking about conjugation, the cyclopentadiene anion. We'll just call it the CP anion because it is there's a way to abbreviate that. All right, let's see if it meets the criteria. So it is flat. It is monocyclic. Is it fully conjugated? If you look back in your notes, when we first started talking about conjugation, you can find the answer to that because I actually showed you how to get to this molecule. Anybody? Is it fully conjugated or not? In other words, is there a p orbital on every carbon?
It's not fully conjugated.
Okay, all right, let's put the p orbitals in. So we know that we got p orbitals here, right? Is that right?
Yeah.
What about the lone pair? Where is it? Is it sitting on the atom, or does it have to be in an orbital?
It's got to be in its own orbital.
It's got to be in an orbital. And for carbon, anytime you have a lone pair on carbon, it's going to be in a p orbital, right? So now we look at the molecule itself and look at the orbitals, we can see that there's a p orbital on every carbon. So it is fully conjugated. Right. Anytime you see a lone pair on carbon, that lone or a plus charge on carbon, that is indicative of either a filled p orbital in the case of a lone pair with a charge, or an empty p orbital in the case of a cation, right, or a positive charge. So how many pi electrons does the CP anion have? That lone pair counts as a pair of pi electrons. So the total number of pi electrons is what? If there are 2 in each double bond, and then a lone pair.
5.
So there are 2 here. And you got 2 here, and then 2 here. So that would be 3.
Oh, 3. My bad.
That's okay. 3 times 2, which is 6 pi electrons. Are you following? Did you catch that? I want to make sure that you got it before we go on.
Yeah, my math isn't mathing today.
That's all right. It's Monday and it's homecoming, so I get it. This is like, for real, for me, like the first time I've ever looked forward to homecoming. It's weird. I guess because I'm on the opposite side of the fence now. But I used to be dreading it because I knew what it meant as far as like the rest of the week is concerned. But it's okay. I'm older and wiser now. I get it. So let's see if we can figure out. So this is 4n plus 2 is 6. So that has the same number of pi electrons as benzene. So you know that n in this case is going to be 1. So that's going to also meet the 4n plus 2 rule. So that CP anion is indeed aromatic. It's actually considered aromatic. The source of that ion, which would be here. I think I showed you this already, which is cyclopentadiene, right? You have to react that with a base to get to that ion. Right? You have to pull off one of these protons right here to get to that. So this is not aromatic. Right? Why wouldn't that be considered aromatic? If we look at the criteria, right? It's flat. It's monocyclic. Would it meet the 4n plus 2 rule? What would n be for this cyclopentadiene? Not the anion, because you have to treat that with a base to get to the anion. What would n be here? If we did, how many pi electrons are here? That's the question we'll start with. If there are 2
2.
pi electrons for every pi bond.
Eight? Is it?
Well,
Oh, wait.
you only have a pi bond here and here. So that's
And you
going to be,
Oh, so
So
4.
it's just 4. You're not counting the carbons, you're counting the bonds itself.
yes.
Okay, because I think that's why I think she got the 8 from, and I was thinking 8 too.
Okay, so let's do it. Let's think about it this way, right? Every bond, whether it's a pi or sigma bond, is made up of 2 electrons, right? So if I have a pi bond between 2 atoms, There's one electron in each, because pi bonds come from overlapping p orbitals. So anytime I have a pi bond, there's one electron in each one of those orbitals, unless it's some type of radical or something like that, right? But for every bond is constructed of 2 electrons and overlapping orbitals. All right. So if you got 2 pi bonds, you just multiply that by 2, and then you'll have the number of pi electrons. So this is 4 pi electrons. All right. So if I this phone buzz one more time. So if I take this and set that equal to 4, what would I have? N would be 1/2, wouldn't it?
Yeah.
Mhm. So what does that mean for the 4n plus 2 rule? Does that meet it?
No,
No. So it doesn't meet the 4n plus 2 rule. And is it fully conjugated?
not in that first step, no.
No, it's not. Right. So does not meet this is to answer this question, that is not aromatic. And the question I ask is why not? So number one, it doesn't meet the 4n plus 2 rule. And then the other criteria that it doesn't meet is that it's not fully conjugated. Not fully conjugated. All right, let's look at the next example. Tell me if that, I want somebody to go through the criteria and tell me if that is conjugated or not. If it's the ring, if it's 7 members, it's going to be planar. It doesn't, those rings don't normally start flexing and bending until you get between like 10 to 13 members. But they start flexing to get to relieve strain. But anything from 3 carbons, a 3 carbon ring up to a 7 or 8, or even a 9 carbon ring is going to be planar. So we know it's planar. What about the other rules?
It is monocyclic.
Good. How many pi electrons? Got 3 pi bonds.
That's 6.
6 pi electrons, good. All right, and what about the conjugation?
Didn't you say a positive on a carbon would be a pi bond?
Well, a p orbital. It's
A p
just
orbital,
empty.
I'm
Yeah,
sorry.
it's just empty. Is that right?
Yes.
So does it meet the conjugation rule of a p orbital on every carbon?
Yep.
Yeah. So this is a cycloheptatriene cation, and it is aromatic. Where it came from is not. Right? Cycloheptatriene itself is not aromatic. It meets the 4n plus 2 rule. It meets the monocyclic rule and the planarity rule, but it's not fully conjugated because this carbon right here it cuts off the conjugation, right? So you have p orbitals on all of these carbons, but not here. So it's not going to be fully conjugated, right? So knowing the rules for aromaticity is important, because you can look at a molecule and put it through these tests to see whether or not it's aromatic or not. All right, so you can, these are your rules for aromaticity, and these are the classical rules. There are exceptions to the planarity, well, not the planarity, but the monocyclic rule. There are no exceptions to 4n+2, and there are no exceptions to it being fully conjugated. It has to be fully conjugated. Any questions about that? All right, let's do one more example. So let's take anthracene. Is anthracene aromatic? What do you think, based on the criteria that have been given?
Yes.
It is, right? What's the let's just go through. It's going to be planar. It's not monocyclic, but it's an exception to that. But it's planar. It is it fully conjugated? We put a p orbital on each carbon in here. Will we have, would every carbon get one? Let's see. Right, so you can see it's fully conjugated. All of those p orbitals overlap. How many pi electrons are there? Got seven pi bonds.
14.
Good. So 14 pi electrons, and if we say 4n plus 2 is 14, n is going to be what? 3?
3?
Yep. So it meets all your criteria. It meets the 4n plus 2 rule. It meets the planarity rule. It's not monocyclic, but it's an exception. And it's fully conjugated. All right. Let's go to much time. We got a few minutes left. So I want to introduce some of the reactions that aromatics do, because I think this is, there's also a little section in here. If you notice, I broke it up in quadrants. So there's a section for nomenclature, which we'll come back to, but what I really want to discuss in detail are these directing effects and the reactions. Right, so I'm gonna cut the reaction part out, put that on the new page, and then we're gonna start talking about that. And if you watch the video, then you kind of saw some of this already, so it's not foreign to you. All right, one of the things I want to point out about benzene and its reactivity is it's basically a brick. Benzene by itself is completely unreactive. The only way you can react it is in the presence of a catalyst, right? Can somebody tell me what a catalyst does?
Speeds up a reaction.
It increases the reaction rate, good, by lowering the activation energy of a reaction, right? So benzene is unreactive without the presence of a catalyst. And there's a reason for that. Right, that aromaticity is such a stabilizing factor, or such a stabilizing it's such a stabilizing force that Benzene would much rather stay by itself and unreactive than it would to react with something. So you got to prod it to react. It won't just react on it spontaneously. All these reactions are endothermic and they all require a catalyst, right? Or they would be endothermic in the absence of a catalyst. So yeah, it's really a non-reactive because it does not want to lose that aromaticity. Right, so every time you react benzene in any situation with a catalyst, whatever you're doing to it, whether you're halogenating it, whether you're alkylating it, acylating it, whatever you're doing to it, one of the final step in all of these reactions is going to be exactly the same. You have to reestablish aromaticity, right? So, and all of these reactions follow the same type of mechanism. And the mechanism is always in 3 steps. So we'll write it out in words and then we'll show it with arrows. Always in 3 steps. The first step is always preparation of your electrophile. In this case, I'm gonna go back and explain that. The second step is attack of the ring on the electrophile. Come on, Russell. And then the third step is to reestablish aromaticity. Every one of these reactions is going to follow this path. So if you see one mechanism, then you can apply that kind of that logic to all of these reactions, right? So these reactions right here, these are examples of what we call electrophilic aromatic substitution, right? It's so the ring is acting as the nucleophile. So when you see the way this will be written is S. You see it written something like that. Sometimes you'll see that used to say that it's nucleophilic aromatic or electrophilic aromatic substitution, it would be E. Sorry. And then if it was nucleophilic aromatic substitution, then the E would be an N. So, all right. So what we're doing in this case is substituting. Let's just look at this example right here. All right, we're substituting a hydrogen on the ring for whatever electrophile you're adding.
I have a question.
Go ahead.
So since it is an aromatic, does it really matter which hydrogen you attack on the ring by any chance?
It doesn't. It doesn't. This is just strictly to keep it coherent so we can see it and understand it. But all of your hydrogens are equally susceptible to being removed. Right. So in this case, you're going to substitute hydrogen with your electrophile. But no, it doesn't, because this is all symmetrical. It does if the ring is substituted. It does matter if the ring is substituted, which hydrogens are more susceptible. Because if the ring is substituted, depending on what it's substituted with, if there's a donor on the ring, then the ortho para, which makes no sense to you now, but let me just go back up to here. Right, so if there's if R right here, and we'll talk more about ortho and para and meta in a second, but if R is a donor, then ortho and para positions get activated. If R is an acceptor, then the meta positions get activated. So it does matter when there's a substituent on the ring, but if there's nothing on the ring, all the hydrogens are equally susceptible and they can all be substituted. Right, so that bromine could literally be, since the ring is symmetrical, it could literally be on any carbon in that ring. But this is strictly to help us keep track of everything. That's a great question, by the way. All right, any other questions? I don't want to push this too far because we only got like a minute left and I don't want to keep you over. Any other questions? We're going to push this more on Wednesday. So make sure you watch that video that I sent. It's going to walk you through the mechanism. And then on Wednesday, we're going to go through each mechanism for each one of these processes. And yeah, it should be, I ain't gonna say fun. Well, it should be fun, but never mind. That's just my inner nerd talking. All right, any questions about anything before we sign off?